The problems playlist has also been updated. The mega problems playlist. It has 59 problems at the moment and more to come. I mean, there's no end to it. Do watch it till content of chapter 6 at the very least. When I will cover chapter 7, which is next week, you will see which problems of chapter 7 you need to also. No, chapter 7 will be there. So you have to do it till chapter 7. Chapter 8 partially will be there. I will share with you the syllabus for the mid-sem I mean later on. Okay, so let's begin. Let's not stand on ceremony over here. So today we will start control volume analysis. First law. So far whatever we have studied is classified as control mass. So all up to chapter 5 whatever we covered was control mass analysis, where the mass of the working fluid was sort of identified, and then we sort of saw how it did boundary work, or boundary work was done on it, how it absorbed heat, how the internal energy changed, and so many things. But often you have systems which are not just piston cylinder systems. You have systems where, say, you have a heat exchanger, hot fluid is coming in, cold fluid is going out, and it exchanges heat. For this case, it's not doing any work. So in this case, it is not entirely convenient for you to identify a control mass. This could be your control mass. There is nothing which prevents you from this being your control mass. But it is more convenient to analyze the problem in this fashion. And it's very much similar to what we had done in fluid mechanics, for those of you who were there in my section at least. So this is identified as the control volume. So the control volume remains stationary. I mean, it could move, it could do whatever, but in most of the analysis we will do in thermodynamics, it would remain stationary, and then you simply track what is going in, what is going out. So what are the things that can go in, go out? So when we say something goes in, goes out, that thing is called as a flux, and this is something which you might remember from your fluid mechanics course. So a control volume can have fluxes of what? So far from what you have studied, it can have a flux of mass, or it can have a flux of energy. Later on you will see it can have a flux of entropy as well. For now it is not relevant. But from a Lagrangian Eulerian viewpoint, Lagrangian and Eulerian, which one is which? I will write down Lagrangian Eulerian, and then I will write down control mass and control volume. Which one is which? This is from fluid mechanics literature. This is from fluid mechanics literature. Anyone?
So Lagrangian is control mass and
Very good.
Eulerian is control volume.
Very good. So this is the one-to-one mapping between fluid mechanics and thermodynamics. And if you look at people who were doing research in the early 1900s all the way to 1960s, you will see that these people had a very good understanding of fluid mechanics, thermodynamics, classical mechanics, and apart from that they were intelligent people, so they could do quantum mechanics. I'm not saying you always need intelligence, but they used to do everything. And the reason is there was not a lot of demarcation between various areas of physics. It was all classified as natural sciences. So anyone who would want to investigate science in its true reality, they would have to know many things. They would not say that, okay, I only know this, I only know analog electronics, or I only know this, I will not work on that. So one must always connect all this to different areas of physics, and the culmination of fluid mechanics, thermodynamics, and all this is in the form of convective transport processes. It's the culmination of all the different thermofluid systems. So let's begin by analyzing conservation of mass. So the most elementary thing that you might recall that you studied in fluid mechanics as well was the conservation of mass, and this would be very simple for you to understand solely because it's not a very difficult concept to grasp. So conservation of mass. So in conservation of mass, we can simply have a control volume like this. This could be a control volume, and you can have some mass coming in, which the flux of which we write as mi inlet, and this could be m dot e. And you don't only need to have one, you can have many. M dot e1, m dot e2, m dot e3, m dot i1, m dot i2. You can have multiple mass influxes into the system and outfluxes out of the system. So the conservation of mass says that the summation of all the input masses minus the summation of all exit masses is equal to something. So what will be that something? What will
Rate
be?
of change of mass in control volume.
Very good. So I will simply write it as dmcv dt. So this is the rate of change of mass in the control volume, meaning this control volume. This is sum of all influxes. This is sum of all outfluxes, effluxes, outfluxes, whatever you want to call it. Okay, and it's as simple as that. There is nothing much to discuss in this apart from this particular concept. But apart from this, a small thing. So if I say that this is a pipeline, and this is a control mass, maybe there's a outlet as well. This is a pipeline, and you have this as the control volume. You can have storage, whatever. So now someone says, okay, I want to relate. Okay, the aim is relate flux of mass to the thermodynamic properties that we know. Let's say that this cross section area is capital A. So first of all, what is the volume flux through this area? So let's say the velocity over here is capital V and the area of cross section is A. So what will be the volumetric flux?
V.
Implied
So velocity times the area. So now what will be the mass flux?
Yeah, maybe.
So it is rho AV. So then in terms of the thermodynamic property that we know, that is the specific volume, I can then write it as AV upon small v. Okay, this small v is the specific volume. Alright, is that okay?
Yes, sir.
Alright, so a quick demonstration of this particular idea. A very quick demo. Let's say you have air flowing in a pipe and the flow rate is, the velocity is, average velocity is 0.1 meter per second. So this is the average velocity. And the temperature is 25 degrees Celsius. And the pressure is 150 kilopascal. So this is just an example from the book, and it's a very good illustration. So the question is, find out the mass flow rate, find out m dot. So m dot will be, so area is given, okay, so it's a 0.2 meter diameter pipe. So m dot will be area times the average velocity. Let's call it v bar. Let's not call it v, because v we are using for the volume of the control volume. So a times v bar over the specific volume. Okay, and what is the specific volume? So let's write down. So area is pi into 0.2 square by 4, right? And the specific volume. So we will use P times the specific volume is equal to R T, where R is the universal gas constant over the molecular weight of air. Okay, so this R for air is 0.287 kilojoule per kg Kelvin. Okay, R for air is 0.287 kilojoule per kg Kelvin. So the specific volume becomes 0.287 times T. So T we must use in Kelvin because this is the ideal gas equation. We must use the absolute temperature scale. So this is 298 approximately, or 298.2 if you want, over 150 kilopascal. So you have to appropriately account for the units. This kilojoule, this kilopascal actually cancel out. You must do this particular calculation on your own. Otherwise, you will not be clear about the kilo cancelling out. Okay. The end unit of this is 0.57 meter cube per kg. I have written it down as 150 kilopascal because this kilopascal kilo and 0.287 kilojoule kilo, they cancel out. Otherwise the units will, it will be SI units, but you will have a kilo floating around. If you do not want to deal with this kilo floating around, what would you have done? You would have written it as 0.287 times 10 to the power 3 joule per kg Kelvin times 298.2 Kelvin over 150 times 10 to the power 3 Pascal. Then you are having all the consistent units. So this cancels out. That is why I did not bother writing them over here. So now with the specific volume at hand and the area known and the average velocity known, you are in a position to find out the mass flow rate. It's a very simple idea. Let's not dwell on this anymore because there is nothing much to it. There is literally nothing much to it. Let's move on to the first law of thermodynamics. For a control volume. Okay, now you can have a very complicated system. Say you have a turbine and the turbine exits to a condensation tank, or there's a small pump which puts it into a boiler. This could be a boiler. Then from the boiler it can perhaps do some piston work, no problem. It could do a bit of piston work. So this is a piston. The boiler, it creates steam, so steam occupies this region, and finally you can have the output of the boiler through a valve. So this can be a entire system, for example. So this is this particular part is a turbine, this particular part is a boiler, this particular part is this piston which pushes is the cylinder where the piston the steam can go and push this piston, and finally you have some exit. Let us draw how one would analyze such a system. Okay, so turbine, when you have stuff coming in, you actually have some work coming out as well. Okay, in a turbine you have high temperature gases or superheated vapor coming in, and the exit is low pressure, low temperature. This is what happens in a turbine. You have high temperature, high pressure. It could be steam or whatever. Finally, low temperature, low pressure. So turbine is a work output. So turbine is typically used in a lot of places like steam power plants, hydro power plants. Okay, so turbine is used to convert that kinetic energy of water or the enthalpy of steam into work. So this also creates work. So now when we draw the control volume, something like this, when we draw the control volume, so it could be encompassing these things, and it could just encompass this. So over here, when the steam goes, you will adjust the control surface so that you are always sort of at the boundary of the piston. This is allowed. There is nothing which prevents you from causing the movement. Okay, so now let us write down. This is not at all a very difficult concept. It is just writing down the conservation of energy for this. So for the turbine, you have some mass coming in, you have some mass coming in. From the boiler, you have some mass going out. Is there any other place where mass is going in, mass is going out? And the answer is no. Let's say to the boiler there is some heat input. There is some heat input. So there is heat input. So Q dot is the rate of heat input to the control volume. Rate of heat input to control volume. Now, what are the different works that are produced? First of all, we have the turbine work, which we classify as shaft work. Okay, so W dot is the rate of production of work. So W dot turbine, it is shaft work, and it is power basically that you take out. So it's like a motor. You extract power with the help of a shaft, a rotating shaft. That is why it is called as a shaft work. Apart from this, any other works that are being done by the control volume?
The piston.
The piston. So we will write this as W dot P. That is W dot P is the piston work due to moving boundary. And we have done this in the previous chapter. Whenever you have the moving boundary, you have a PDV work, right? So this work will still be integral PDV. Okay, there is nothing that's going to change, because what is this P going to be? It is the pressure due to the piston on top. The piston is being moved against this pressure. This pressure need not be a constant, as we have seen in various kinds of examples. Alright, so now, what was the first law for a control mass? First law for control mass. In statement form, it was total change in energy was equal to heat input to the system minus work done by the system. So we can write it as E2 minus E1, pardon me, is equal to Q12 minus W12, where E comprises of what? I have told this previous time. E comprises of the internal energy plus half mv square plus
potential
mgh. But in all the problems where we had control masses, we had something like a piston cylinder arrangement. So this mass was not suddenly moving at a very high velocity, nor was the mass being elevated to a significant height. And because of this, this contribution and this contribution were neglected. They were neglected. They are not zero, but they are neglected in comparison to the actual change in internal energy. Therefore, we often wrote this as U2 minus U1 equal to Q12 minus W12. This is often what we wrote the first law for a control mass as. But one should always remember there is always a half mv square and a mgh. When can the mgh become significant? Say on top of this piston, there is a platform on which there is a massive car. Okay, this is a car. You imagine this is a car. So you are hitting the piston and the car is being lifted. So if you consider this as the entire control mass, then you have an mgh over here as well. Okay, so in such situations you have to apply your elementary mechanics. So whatever you have studied in class 11, all those H.C. Verma kind of things where there's a monkey hanging on by another monkey's tail. So all that kind of stuff is accounted in this and this. All right, so this is for a control mass, but what happens for a control volume? You have stuff coming in, stuff going out. So we must now adapt whatever we have studied for all this to account for the fluxes of mass. So let me just grab hold of all this and then we can analyze it over here. So over here we will write that the rate of change of total energy of the control volume, okay, what is this going to be? So this expression is the rate of change of energy of the control volume, the energy contained in the control volume. So what is this going to be equal to? So let us take a step back and see what are the things that are contributing to the rate of change. The first contributor is some mass that is coming in, and this mass will bring some energy with it. This mass will bring some internal energy, and this mass will take away some internal energy. Do you agree with this?
Yes, sir.
Yes.
Apart from this, you have some heat input to the system and some work output from the system. This is work done
by the system.
by a control volume. This is work done by a control volume. So we must, let us write it down in words. So it is energy fluxes in minus energy fluxes out plus heat fluxes in minus what? Work out. Okay, so when we have this, we can simply now write down dECV dt is equal to m dot summation of m dot I. So what is the total energy? So let's do it step by step. Don't have to do it in one go. So I can write down m dot I EI minus summation of m dot E EE plus Q dot minus W dot. Okay, is that clear? We have done nothing but written down the mathematical form of whatever we have written in words. Is it fine so far? Hello?
So what is the small e?
Yes, sir.
Small e is the total energy coming in. So small e is going to be the specific. So look, small e is the specific total energy. Very much like this. The total energy was total internal energy plus kinetic energy plus potential energy. What is small e going to be? It is capital E over mass. So that is going to be the specific internal energy plus half V square plus Gz. It is the total quantity divided by mass. That is the same definition of the specific quantity. Okay, is that fine?
Yes, sir.
Okay. So it will be U plus half V square. V is the velocity plus Gz. Anyway, so you have dECV dt is equal to summation of all fluxes coming in ui plus half v square plus gz minus summation of all the exit energies ue plus half v square plus gz plus all the heat transfers minus all the works done. Now here is a very subtle part. This work done, what kind of contributions does the work done have? We have already seen it consists of any boundary work, and we have already seen it consists of any kind of shaft work. But there is something else that we are missing. And what exactly are we missing? What are the contributions to expression for W dot? So W dot we have already seen is W dot boundary plus W dot shaft plus there is something called as flow work. What is flow work? Imagine this is a control volume and you have a pipeline coming in. When there is flow coming in, the control mass, if I imagine this to be a control mass, when it has to go into this control volume, the pressure in the pipeline, which is say Pi, that is the inlet pressure, has to sort of push it in. So any incoming line, it is doing work on the system. It is pushing this imaginary mass into the volume, control volume. And what is the amount of work? It is going to be Pi, or let us write down the entire expression slowly. So the work done by this in pushing this mass into the control volume, the rate of work done will be force times the average velocity. This is work, rather power. Rate of work done is what? It is power. That is power equal to force times the velocity. Is that fine?
Yes, sir.
Does everyone remember this? Otherwise, H.C. Verma will be very sad. You've forgotten this. You remember this, right? Rate of work done.
Yes, sir.
Ah, good.
Yes. Yes, sir.
Otherwise, I would have asked you to appear for JE again. So, force in terms of pressure is what? Now look, this force is being exerted by whatever the pipeline pressure is, and it is being pushed. So it is like you have this piston, you have this pressure, so it is pushing this piston outside. So it will be Pi multiplied by the area. This is the force multiplied by the average velocity. So what is this going to be? It is going to be Pi times, I can write this as area times the average velocity over the specific volume at the inlet times the specific volume. What is this expression?
Mass flux.
It is the mass flux. Okay, so the rate of work done on the system, okay, this is work done on the system is this. So the flow work W dot flow for the incoming line is equal to what? It is work done on the system, so it is negative. So it is going to be minus Pi Vi times m dot I. Is this clear to everyone?
Yes, sir.
For the others, in case this is not clear, you please look at the recording once again. The idea is very simple. The pressure in the pipeline is having to push with this pressure into the control volume. Okay, that is the logic. So
So,
now, yeah, please.
so for outgoing, it will be positive or what?
Yes,
The
yes, yes.
same.
I'm doing that. I'm doing it. हौसला रखो, हौसला रखो. So this we bring it over here. Now let us do the analysis for the outgoing. Say this is the outgoing. So this is the outlet pressure is P exit. Now when the mass is going out, it is as if the system is pushing it against. So outgoing line, system is pushing against PE, meaning for the same analogy, this is PE and you are pushing this piston against this PE. So what is the work done by the system? So this work is going to be by the system. Work done by the system. And what is
Positive.
it going to be? So it is going to be W dot is equal to force times the average velocity at the exit. So this is going to be P at the exit times the area at the exit. So this is inlet, this is inlet. Don't be confused. Because this pipeline can have a different diameter, this pipeline can have a different diameter. Okay. So this is volume at, this is velocity at the exit. Simply I can apply the same logic. I can have PE, small ve, AE, average velocity over specific volume. Now the bracketed term is the exit mass flux. So this becomes PE, VE, M dot E. Okay. So the W flow out is work done by the system, and that is why you have this as positive PE, VE, M dot E. Okay. These are two very fundamental results, and we will see how these expressions tie in very nicely with the idea of enthalpy in a moment. Okay, these two results are very important. And I know what you're thinking, that in one case I took the internal pressure, in one case I took the external pressure. But remember, even at this point, I will assume quasi-steady. Even if the system pressure is something different, when the fluid is just trying to go out, the pressure over here will be just close to PE. The pressure over here will be just close to PI at the boundary. It will be something very close to PI. It will be something very close to PE. When I say something very close to PI, should it be larger than PI or should it be lower than PI? Slightly larger or slightly lower? Tell me. Not Anirudh Bajaj or Sai Saran Venkat. Someone else should tell me. This inlet pressure in the system, will it be slightly lower, slightly higher, or exactly equal to PI? And the exit pressure, will it be slightly equal, slightly lower, slightly higher than the actual exit pressure? That girl will tell us. Saili. Saili, you're not in class.
Sir, in the class, I'm not
So,
clear with this concept.
so
So I have
if there is some pipeline pressure which is pushing fluid into the system, okay, what do you think at the boundary, will the pressure be higher or lower? If let us say, Saili, you don't know what the answer is. Let us break down the problem. If the pressure at the boundary in the system, if pressure in boundary at the system is larger than Pi, can the mass enter into the system, Saili?
uh,
Let
if
me
the
draw it.
outside pressure is greater than PI, right?
If this is Pi and this is just Pi at the boundary in the system, this I am asking, will it be larger than this or smaller than this? Option A, larger, option B, lower, option C, equal. Which sign should come here? If P boundary is larger, then there cannot be a flow here, na? In fluid mechanics, you have learned this. This pressure has to be larger than this so that there is a flow in this direction.
Yes, sir.
Or is it still not clear?
It's still not a bit clear. I'll have to look at
Let's
recording
say,
again.
let's say you have had Pepsi through the bottles.
Yes.
Suppose this is Pepsi. You want to draw Pepsi. So should the pressure here be lower or pressure here be higher than this pressure? So this is 0.1, 0.2. Which pressure should be higher?
Point two.
If pressure at 0.2 is larger, then you are blowing air into the Pepsi.
Okay.
So pressure at 0.1 has to be higher. So we know that flow happens from what? Higher pressure or lower pressure?
Higher pressure to lower pressure.
So this is high, this is low. So now tell me,
Yes, from
with
1
that
to
in
2.
mind, with that in mind, this is PI,
Hmm.
this is PI
PI
at the
outside
boundary.
will be greater.
So
Yes.
finally, now you get it completely.
Yes, sir.
Now tell me this PE at the boundary, will it be slightly higher, slightly lower, equal to this PE actual in the pipeline?
PE inside will be greater than PE out
Very good. So
because
she gets it. Okay, fine. So now I know that you have got it and you have deconstructed the problem. So by now everyone should also get it. Okay. So now let us combine everything inside this expression. Let me copy this expression. Guys, it is not difficult. I don't know what you're thinking right now, but we are literally just doing checks and balances. Do you understand what I mean by checks and balances? Has anyone heard of the phrase checks and balances? This is how much money stays in your bank account. This is how much salary you get. This is how much money spending you do. This is how much your parents give you. This is how much you give to your parents. And the flow work is interest charged. Okay? This flow work is like interest charge. Acha, you want to put some money in the bank, give me some commission. It's something like that. Okay? You have to do it, otherwise, you cannot put the money in the bank. It is not there in our system, but you get the point. Have I made all the financially inclined people also clear what is going on? Let me just put it this way. If you want to deposit money, you have to do some work. If you have to withdraw some money, the bank does work on you. Okay? It is something like that. So now this W dot will now comprise of the following: minus W dot boundary plus W dot shaft minus P inlet summation of all the P inlets, specific volume inlets, Mi dots, plus summation of all P exits, specific volume exits, Me dots. So PV, this is the PV work. This is not integral PV work, but this is PV work. It's not integral PDV, huh? So this PV work is known as flow work. This is specific flow work. When you multiply it with the mass flux, this specific term goes away. Okay, when you multiply it with the mass, okay, Pi Vi is the specific flow work, and when you multiply this by the mass flow rate, it becomes the total work done. Okay, so that is why this expression is how it is, and we have done this small derivation to arrive at these things. So now let us combine the different terms. Let us take this term and this term. Let us see what we get. Let me write it in green. So we have summation m dot I ui plus pi vi plus half vi average square plus gzi. Let us combine this and this. What do we have? We have minus summation of m dot e ue plus PEVE plus half VE average square plus GZE. Okay. Then remaining is what? And the remaining is standard. It's plus Q dot minus all the W dots, no flow work. Because the flow work has been accounted for. So this W dot, it solely comprises of the boundary works and it comprises of the shaft works. Now, who can tell me what this fellow is? What, okay, probably the contrast is what this fellow is. This and this.
Enthalpy.
Enthalpy.
Very good. It is the enthalpy. So we have summation m dot I hi plus half vi average square plus gzi minus summation of m dot e he plus half ve square plus gze plus q dot minus w dot. Okay, I am gonna repeat this again in benefit of everyone. The incoming flow, let us analyze this term. The incoming mass flux, listen to this very carefully. Incoming mass flux is bringing along with it some internal energy, some specific internal energy. It is having some incoming velocity. Suppose the incoming pipeline has fluid coming in at a very high velocity. So that is the incoming specific kinetic energy. This is the incoming specific kinetic energy, and this is the incoming specific potential energy. Okay. And what is this term? It is the specific work done by the incoming mass in order for the incoming flow to enter into the system. It is the specific work done by the incoming mass in order to enter into the system. Is this clear? Whatever I just mentioned, is this clear? Any question you ask?
Sir, can you repeat once?
Let me repeat it once. In fact, I will write it in big so that when you have the notes in front of you, you can quickly associate. This is the expression for the total incoming energy into the system. Total, in totality. It comprises of the mass flux times all the specific quantities. All the specific quantities which the mass flux is bringing into the system. What are the specific quantities that we know from common sense that the mass flux is bringing? It is bringing specific internal energy, specific internal energy. It is bringing specific kinetic energy, and it is bringing specific potential energy. When you multiply the specific quantities by the mass flux, you get the total quantity. I'm repeating it again. But apart from this, the other thing that the incoming mass flux also has to do is to push that mass into the system, and in doing so, that incoming mass flux also has to do a specific flow work, which originally was accounted in the expressions for the work done, but we took it out from the expressions of the work done and combined it with this mass flux, so that you have a combination of terms U plus PV appearing. So the combination of specific internal energy U plus specific flow work, that is PV, gives rise to specific enthalpy. And therefore this expression can be written as summation mi dot hi plus half vi square plus gzi. In writing so, we have implicitly built in the fact that apart from bringing specific internal energy into the system, you are also accounting for the specific flow work being done by the incoming mass flux, and that culmination is through the specific enthalpy. Now is it clear
Yes, sir.
to everyone?
Yes, sir.
Yes, sir.
So the usual people have nodded. What about Saili?
Yes, sir.
Are you sure?
Yes.
That was not a very confidence instilling yes, but don't worry. When we do problems, it will be absolutely crystal clear. Okay, when we do problems, it will be absolutely crystal clear. So for now, you write down the total balance again. dECV dt is summation of all heat fluxes into the control volume minus summation of all works by the control volume. This only consists of shaft and boundary work. All the flow work has already been taken care of in defining the enthalpy. So this will be plus summation of all the mass fluxes coming in, which, so all the mass fluxes that are coming in, what are the contributions of the mass fluxes coming in to the rate of change of internal energy? Enthalpy plus half Vi square plus Gzi minus whatever mass flux is leaving the system is taking away with it a certain amount of enthalpy at the exit condition plus half VE square, pardon me, plus GZD. Okay, how do you interpret this expression? That when the mass exits, it takes away the specific internal energy at the exit condition. It takes away the specific kinetic energy at the exit condition. It takes away the specific potential energy at the exit condition. But at the same time, the boundary has to push that mass out of the system. And in pushing that mass out of the system, it does a work equal to PeVe. It does a specific work equal to PeVe, which when you multiply with m dot E, you get the total work done in pushing that mass flux out of the system. Say you are an unwanted person in my office. I want to push you out. I need to actually push you out. I cannot just say you go, you will not go. I need to actually do some work on you to push you out of the system. When you want to come into my office, you have to push me to go into my office. So essentially you are doing work on me, and while exiting, I am doing work on you. Try to understand what is going on. Masses simply do not come in, go out. They have to do flow work at the boundaries. Am I able to give you enough analogies? So when you combine these two, you get the specific enthalpy at the exit, which is what we have written over here. And in more concise form, we can write this as Q dot CV minus W dot CV plus summation M dot I HI total minus summation M dot E HE total. So HI total and HE total account for the specific the specific enthalpy plus the specific kinetic energy term plus the specific potential energy term. HE total also accounts for the specific enthalpy at the exit plus the total specific kinetic energy plus the total specific potential energy. Have I made myself clear?
Yes, sir.
Yes, sir.
Guys, I'm running out of breath in explaining this with such a high degree of energy. Let me drink some water. Oh, I'm out of water. Anyway, so is this clear?
Yes, sir.
Yes, sir.
Okay. Now let me just juxtapose the mass conservation on along with this for a quick comparison. So dmCv dt is equal to summation m dot I minus summation m dot E. That is it. Now let us look at a very special case. So the special case, we have done that in fluid mechanics as well. That is steady state. At steady state, this term becomes 0. This term also becomes 0. And that is quite obvious. So what does it mean at steady state? Let us write down the conservation of mass. Let me write this as equation 1. So equation 1, it tells 0 equal to summation of all mass flux minus summation of, oh come on. Okay, and essentially if you rearrange this, you get m dot I summation is equal to summation m dot E. So all the mass fluxes coming in is equal to all the mass fluxes going out. And this should be very, very obvious. Yes?
Yes, sir.
Now let us look at the first law. What happens for the first law? So 0 is equal to summation of all the heat transfers to the system minus summation of all the works done by the system. I don't know why I'm putting this dot on top of the summation. Okay. Plus summation of all m dot i's hi total minus summation of all m dot e HE total. Let me rearrange this. So we have summation of Q dot CV plus summation of M dot I HI total is equal to summation of W dot plus summation of M dot E HE total. Meaning whatever heat you transfer to the system, Q dot 1, Q dot 2, and whatever energies are incoming into the system, M dot 1 HI total, M dot 2 HI H2 total, whatever incoming, that has now given this control volume an ability to do works. Okay, these are the additions into the system. With this, you can do works and you are also losing fluxes through the enthalpy at the exits. Okay. So if these are not there, you will not be able to do work and you will not be able to extract some enthalpy out of the system. These are the inputs. These are the outputs. Okay. Is it clear? We will use this in solving problems. The problems are very easy, but you must understand things at a conceptual level. Unless you understand things at a conceptual level, it will be very difficult for you to approach problems in a very free mind. You will always be in a state of dilemma on what to do. But if you follow the concepts, you will be in a very good footing. You don't need to practice a huge number of problems. Of course, practicing is always good, but if the concept is there, you can do the problem at your own pace. If the practice is there, you can do the problem at very fast pace. That is the only difference. But if concept is not there, you can do the problem at a very fast pace, but it will be incorrect. It will not fetch you any marks. That is how it works. Okay. So concept and practice is necessary. But today you have to join me at 9:30 because we will do problems on this. So everyone, please find 40 minutes time and join me for this compensatory problem solving class. It is in your own benefit. Let me save this file so that I can give it to you for your practice. So this will be lecture control volume first law. I will give this to you. And someone asked the other day that what is this software? So it's called as Zernal++, as you can see in the title bar also. It's a free open source software. It is cross-platform. You can run it on Linux, GNU Linux. You can run it on Windows. You can run it on Mac. You can compile it from source if you like, if you're so inclined to do so. Okay, guys.
Yes, sir. Thank you, sir.
All right.
Thank
So
you.
I'll see you. I'll
Yes,
see
sir.
you at night. Okay. Please find the time.
Yes, sir.
Okay, okay, sir.
Yes.
Thank you.
All right.
Thank you, sir.
Have a good day.
Okay. Thank you.
Take care. Bye.
Thank you, sir.
Thank you, sir.
Thank you.